Example 21.4, part E and F, wants us to continue looking for the exact solution. We have to be sure to reject any values of x that are not in the domain of the original logarithmic expressions, and then we'll get a decimal approximation for our exact solutions as well. Part E, on the left-hand side, has two logarithmic statements with an addition operation between them, and on the right-hand side we have a constant of 1. Now, in order to be able to do the one-to-one property, I have to have a single log on the left and a single log on the right. Now that might mean that we could just take the log here on the left and move one of them over here to the right, and then we'd fix our problem. But we would not be dealing with the constant of 1 if we were trying to do that. So the one-to-one property ends up not being available to us because of that constant of 1. If it wasn't for that constant of 1, then we could get away with just separating the logs and then using the one-to-one property. But I can still take whatever I have here on the left and I can still condense them together, so that way it just is represented by one single log. So this would be log base 6 of x plus 3 times x plus 4, all equal to 1, which would be the same as saying log base 6 of x squared plus 7x plus 12, all equal to 1. And now I can use my definition for log exponential equivalency, and I can write this as 6 to the first power is equal to x squared plus 7x plus 12. In which case, 6 to the first power is really just 6, and now I have a polynomial equation, and I can subtract 6 from both sides to be able to get the polynomial in standard form, x squared plus 7x plus 6 now, and this is nothing more than just a quadratic equation. You could use quadratic formula if you were so inclined. However, this is a nice enough quadratic equation that I can perform trinomial factoring with x plus 6 and x plus 1. And then setting each factor equal to 0 should give us two possible results: x equals negative 6 or x is equal to negative 1. If you take negative 6 and plug it back in to either one of the two original logarithmic arguments, it's going to fail. So x equals negative 6 is not going to work. But if you plug in x equals negative 1, neither one of those logs is going to have an issue with that. So x equals negative 1 ends up being the only solution that we have for this equation. Part F, we will look at this one in a similar way that we did with part E, because we have two logs and we also have a constant term. So very similar here, but the two logs are already separated on opposite sides of the equal sign. But again, because of this constant, this extra plus 2, I can't directly apply the one-to-one property. Even if I did take the coefficient of 2 and bring it up, I still wouldn't be allowed to do that. So let's look at it a little more closely. The second log in particular, log base 3 of 9. That logarithmic statement has no variable in it whatsoever. In fact, that is a logarithm that is nice enough that you could evaluate it without the use of a calculator. That particular logarithm is equivalent to 2. So really what you have on the right-hand side is the statement 2 plus 2. You don't have to have a log there at all, in which case we would say 2 log base 3 of x plus 4 is equal to 4. And just like on one of the previous parts, you do now have the option, if you wanted to, you could take this coefficient of 2 and you can bring it up as a power, or we can divide both sides by 2, getting the 2's to cancel on the left hand side and making the constant on the right a little bit smaller. So this would become log base 3 of x plus 4 is equal to 2. Now I can use the definition for log exponent equivalency, and this is going to read 3 to the second power is equal to x plus 4. So therefore 9 is equal to x plus 4, giving us that x is equal to 5. And substituting that into the original equation, back up here where you have the x plus 4 argument, presents no problem. So we'll box this in as our only solution.